Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Welcome to episode 8 of Kubernetes Production Mastery. Last episode, we built observability, Prometheus metrics, 4 golden signals, logging with Loki. You can finally see what's happening in production. But here's what those metrics also reveal. Waste. Your Prometheus dashboard shows pods requesting 4 CPU cores. Actual usage, 0.3 cores. Dev clusters running 24/7. Nobody logged in after 6 p.m. or on weekends. 20 different clusters, each with its own load balancer, monitoring stack, networking overhead. Then your CFO walks in with a question. Why did our Kubernetes costs triple this year? Here's the uncomfortable truth. Kubernetes costs grow year over year for most organizations, not because workloads actually grow, because waste compounds. Every over-provisioned pod, every idle development cluster, every "we might need 5 replicas just in case," it all adds up. Today, we're fixing that. By the end, you'll identify the 5 sources of Kubernetes cost waste ranked by impact. You'll right-size resources using actual utilization data from Episode 7's Prometheus and tools like Vertical Pod Autoscaler, and you'll implement cost controls, resource quotas, cluster autoscaling, spot instances that prevent waste before it happens. Let me show you how this spirals. You start with 1 production cluster. Makes sense. Then you add staging for testing, then dev for development, then per team clusters because teams want isolation, then a disaster recovery cluster. 20 clusters later, your bill is out of control. Why? Because each cluster has baseline costs, control plane nodes, monitoring infrastructure, load balancers, networking. And these clusters don't share resources, no multi-tenancy. Dev clusters are provisioned like production, over-provisioned for just in case. Nobody's explicitly responsible for cost optimization because feature work takes priority. Here's the typical breakdown. Jobs and cron jobs waste 60 to 80% of resources. Stateful sets waste 40 to 60%. Overall, most organizations waste 30 to 50% of their Kubernetes spend on over-provisioned resources, idle clusters, and missing autoscaling. Over-provisioned resource requests are the biggest culprit at 40 to 60% of total waste. Idle resources, dev clusters nobody's using, another 20 to 30%. And lack of visibility means you can't optimize what you can't measure. Think of it like this. Kubernetes is a fleet of trucks. You ordered 10-ton trucks for every single delivery, but most of your deliveries are 50 pounds. You're paying for 10 tons of capacity using 50 pounds. That's over-provisioning in a nutshell. Now, here's where it gets interesting. This isn't malicious. Engineers aren't trying to waste money. You're optimizing for the right thing, resilience and performance. That's your job. But unchecked, it leads to over-engineering. Examples I see constantly. We might need 5 replicas. Currently, you need 2, but you're planning for growth that hasn't happened yet. Let's add a service mesh. Great for complex architectures. But now you have 200 sidecars times 50 megabytes each equals 10 gigabytes of overhead. Run dev 24/7 in case someone needs it at night. Paying for 168 hours per week, actually using 40. Remember episode 2? Resource requests reserve capacity. You pay for reservations, not actual usage. Over-request equals overpay. That's the core problem. Let's break down the 5 cost waste sources. Source number 1 is the biggest. Over-provisioned resource requests. Pods request 4 CPU cores, use 0.3. Request 8 gigabytes of memory, use 1.2. Why does this happen? Developers guess at requirements. 4 cores should be safe. They copy-paste manifests from tutorials. Those are examples, not recommendations. There's no feedback loop. Nobody checks actual usage after deployment. And there's fear of out-of-memory kills, so everyone requests 10 times what they actually need. The impact is massive. This is 40 to 60% of total waste. 100 pods times 4 CPU requested times 3.7 CPU wasted per pod equals 370 wasted cores. At 5 cents per core hour, that's $16,200 per month of waste from a single application. Remember Episode 2's quality of service classes? Guaranteed versus burstable? Over-requesting puts you in guaranteed. You pay for that guarantee whether you use it or not. Source number 2, missing resource limits. When pods don't have limits, they can consume unlimited CPU and memory. Eventually, the node runs out of resources. You get evictions, noisy neighbor problems. Why is this a cost issue? Because you can't pack pods efficiently when their resource usage is unpredictable. You must leave large buffers on nodes. That's wasted capacity. And you can't use node autoscaling safely because pods might unexpectedly consume resources and trigger unnecessary scaling. The fix is setting limits at the namespace level with LimitRanges. This prevents anyone from deploying pods without limits. Source number 3, idle resources. Your development cluster has 20 nodes, runs 24/7, but developers actually use it 9 a.m. to 6 p.m., Monday through Friday. That's 45 hours per week of usage. You're paying for 168 hours. The waste is 73% idle time at full cost. Real example, development cluster costs $5,000 per month, used 27% of the time. Waste, $3,650 per month, just sitting there. The fix is cluster autoscaling to 0 when nobody's using it, scheduled scale down after hours, or ephemeral clusters per pull request that get destroyed when the PR closes. Source number 4. No autoscaling means paying for peak capacity always. You provision for Black Friday, for end-of-month report generation, for that 2-week spike every year. Then you run that same capacity year-round, 12 months of bills for 2 weeks of need. The fix is horizontal pod autoscaler for pods and cluster autoscaler for nodes. Scale up when you need it, scale down to baseline when you don't. Example, baseline 10 pods, peak 50 pods. Without autoscaling, you pay for 50 pods always. With autoscaling, you pay for 10 baseline plus 40 pods only during peaks. Source number 5, lack of visibility. No cost metrics means no optimization. You don't know which namespace costs the most, which team is over-provisioning, whether your cost trend is going up or down, where to focus your optimization efforts. This is where tools help. KubeCost shows per namespace, per deployment, per pod costs with specific savings recommendations. Cloud Provider Cost Explorers, AWS Cost Explorer, Google Cloud Billing, Azure Cost Management break down spending by resource type. And remember Episode 7's Prometheus? It's not just for alerting, it's for cost optimization. Compare container CPU usage to pod resource requests. The difference is waste. The formula is simple. Waste equals requested minus used. Prometheus gives you both sides of that equation. Now let's talk about right sizing. Here's the process. First, query Prometheus for actual usage over 7 to 30 days. You need a realistic baseline that includes peaks. Second, compare actual usage to resource requests. Third, identify candidates, pods with more than 50% waste. For example, requesting 4 CPU but using less than 2 consistently. Here's the PromQL query. Average resource requests over 7 days minus average actual usage over 7 days divided by average requests. This gives you waste percentage. What should you look for? Consistent low usage. Request 4, use 0.3 always, means you should reduce requests. Occasional spikes. Use 0.3 baseline, but spike to 2.5 during peaks, means reduce requests but increase limits to allow bursting. High variance with unpredictable usage means keep current settings or use Vertical Pod Autoscaler for dynamic adjustment. Speaking of VPA, it watches pod resource usage and recommends requests and limits. It can even automatically apply changes, though that requires restarting pods. VPA has 3 modes. Off mode gives recommendations only with no changes. This is the safest place to start. Initial mode sets requests when pods are created but doesn't change running pods. Auto mode updates requests dynamically by restarting pods. For use cases, run VPA in off mode first. Get recommendations, manually review them, apply selectively. For hands-off automation, use auto mode, but only for stateless workloads that handle restarts gracefully. Example output. Pod X requests 4 CPU. VPA recommends 1.5 CPU because P95 usage is 1.2 CPU. The caveat is that VPA restarts pods. For stateful workloads or high-traffic services, use the recommendations but apply them manually during maintenance windows. Don't let VPA restart your database in the middle of the day. But you can't just cut resources blindly. You must validate performance under load. Here's the process. Apply reduced resource requests in staging first. Run a load test simulating production traffic plus a 20% buffer. Monitor latency P95 and P99. Error rate, pod restarts, CPU throttling. If metrics stay healthy, apply to production. If performance degrades, increase the requests. Let me walk through my thought process on a real change. Reduced API service requests from 2 CPU to 1 CPU based on VPA recommendation. Ran load test. P95 latency increased from 50 milliseconds to 75 milliseconds, still under our 100 millisecond SLO. Deployed to production. Monitored for a week. No issues. Success. That's 1 CPU per pod, times 20 pods, times 24 hours, times 30 days, times 5 cents per core hour. Savings, $720 per month. The key is being iterative. Don't cut all resources by 50% across the board. That's a recipe for outages. Pick 3 to 5 highest waste workloads, right-size them one at a time. Monitor each for a week before moving to the next. Priority order matters. Start with development and staging environments. Low risk, high impact. Then, batch jobs and cron jobs. They're restartable and forgiving. Then, stateless production services that can scale and handle restarts. Finally, stateful production services. These need the most care. Now, let's talk about cost controls that prevent waste before it happens. Resource quotas operate at the namespace level. They cap total resources a namespace can request. Example, development namespace limited to 50 CPU and 100 gigabytes of memory. This prevents runaway resource requests and forces teams to stay within budget. LimitRanges operate at the per pod level. They enforce minimum and maximum requests and limits per container. Example, containers must request 0.1 to 4 CPU and have limits between 0.1 and 8 CPU. This prevents missing requests and limits. It also sets sane defaults for pods that don't explicitly specify values. Use these together. Limit ranges ensure every pod has requests and limits. Resource quotas ensure the namespace doesn't exceed its budget. Concrete example. Limit range sets default 500 millicores CPU with max 4 CPU per container. Resource quota caps namespace at 20 CPU total. Result? Each pod gets 500 millicores by default, can't exceed 4 CPU, and the namespace maxes out at 20 CPU total. That's a maximum of 40 containers. Cluster Autoscaler adds and removes nodes based on pod scheduling needs. Pods pending because they can't schedule? Add nodes. Node underutilized and you can reschedule pods elsewhere? Remove the node. The cost impact is significant. Pay only for the nodes you actually need. Baseline, 5 nodes. Peak, 20 nodes. Average over the month, 8 nodes. You pay for 8, not 20. You configure it with minimum and maximum node counts, scale down delay for how long a node must be underutilized before removal, and resource thresholds for triggering scale decisions. Remember Episode 2's node pressure eviction? Cluster Autoscaler prevents that by adding capacity before you hit limits. Spot instances are spare cloud capacity, 60 to 90% cheaper than on-demand pricing. The catch? They can be reclaimed with 2 minutes notice. Use cases: batch jobs that can retry if interrupted, CI/CD builds that are stateless and retriable, data processing that's checkpointed and resumable. Don't use spot instances for stateful databases. Interruption equals data risk. Don't use them for user-facing APIs. Interruption equals downtime. Don't use them for critical long-running processes. The pattern is a mix. On-demand instances for critical workloads, spot instances for batch and retriable workloads. Real example, data pipeline costs $2,000 per month on demand. Switch to spot instances, $400 per month. That's 80% savings. Interrupt rate is 5%. Jobs retry automatically. Well worth it. Now here's the dilemma every senior engineer faces. Your instinct says, what if we need it? Design for the worst case. Plan for growth. Add redundancy. That's good engineering. But the cost-conscious perspective says, do we need it now? Pay for what you use, scale when necessary. Both viewpoints are right. The question is, where's the balance? Let me give you a decision framework. Service mesh example. Question, do we need a service mesh? Cost, 200 pods times 50 megabytes per sidecar equals 10 gigabytes of overhead, plus operational complexity. Value, MTLS for security, observability for distributed tracing, traffic management for canary deployments. Decision, do you have compliance requirements mandating MTLS? 50-plus microservices with complex routing needs? If yes, value exceeds cost. Deploy it. If no, defer until you actually need it. Replica count example. Question, 3 replicas or 5? Current load handles easily with 2 replicas. Cost, 3 replicas equals $300 per month, 5 replicas equals $500 per month. Decision, start with 3. Add horizontal pod autoscaler to scale to 5 during peaks. Average monthly cost, $350 instead of $500 flat. The pattern is, start conservative with lower cost. Add autoscaling as your safety net. Scale when data shows you need it, not just in case. Remember Episode 1's production readiness? It requires resilience. Episode 6 covered service mesh for complex architectures. The question isn't, is this valuable? The question is this valuable now, or can we defer until we have data showing we need it? Let me walk through common mistakes. Mistake 1, optimizing production first. What happens? High risk of outages, team resistance, potential customer impact. The fix? Start with dev and staging. Low risk, builds confidence, proves your process works. Mistake 2, cutting resources without monitoring. What happens? Silent performance degradation, eventual outages, rollback and loss of trust. The fix? Monitor during and after changes. Watch latency, error rate, CPU throttling. Mistake 3, no resource quotas in dev and staging. What happens? Developers over-request in dev because there's no cost pressure. Then they promote to production with the same over-provisioned values. Waste continues. The fix? Quotas everywhere. This forces right-sizing early in the development cycle. Mistake 4, ignoring idle times. What happens? Dev clusters run 24/7. Paying for 168 hours per week, using 40. The fix? Cluster autoscaler to 0, or scheduled scale down after business hours. Mistake 5, optimizing once and forgetting about it. What happens? Workloads change. Requests no longer match actual usage. Waste creeps back in. The fix? Monthly review using Kubectl or Prometheus. Continuous right-sizing. Let's pause for active recall. First question, what are the 5 sources of Kubernetes cost waste and which is typically the biggest? Second question, your dev cluster costs as much as production. What are 3 things you'd investigate first? Third question, name 3 cost optimization techniques you could implement tomorrow with low risk. Here are the answers. The 5 waste sources, over-provisioned requests is the biggest at 40 to 60% of waste. Missing limits, idle resources, no autoscaling, lack of visibility. For the dev cluster investigation, is it running 24/7 versus actual usage hours? Are resource requests copy-pasted from production and therefore over-provisioned? Does it have resource quotas, or are teams allowed to request unlimited resources? For low-risk optimizations starting tomorrow, install Kubectl or enable cloud cost visibility. This is 0 risk and gives you pure insight. Set resource quotas on dev and staging namespaces. Low risk, immediate cap on waste. Right-size 3 to 5 highest waste non-production workloads using VPA recommendations. Low risk, measurable savings. Let's recap. 5 cost waste sources ranked by impact. Over-provisioned requests at 40 to 60%. Idle resources at 20 to 30%. No autoscaling, missing limits, and lack of visibility. The right-sizing process, analyze Prometheus metrics showing actual versus requested resources. Use VPA recommendations. Validate with load testing. Roll out iteratively, starting with lowest risk environments. Cost controls. Resource quotas. Resource quotas cap namespace budgets. Limit ranges set per pod defaults and maximums. Cluster Autoscaler scales nodes based on actual demand. Spot instances cut costs 60 to 90% for batch workloads. The over-engineering balance. Start conservative. Add autoscaling for safety. Scale when data shows you need it, not just in case. And this is a continuous process, not one-time optimization. Monthly reviews. Adjust as workloads change. This connects to previous episodes. Episode 2's resource requests and limits now have cost implications. Over-request means overpay. Episode 7's Prometheus metrics enable cost analysis. Usage versus requests equals waste. Episode 1's production readiness checklist includes cost optimization as a requirement. You can now build infrastructure, observe it, and optimize costs. Next episode, GitOps and deployment automation. Manual kube control apply doesn't scale to 20 clusters. We're covering Argo CD versus Flux for GitOps, Helm versus Customize for configuration management, and deployment strategies beyond rolling updates, canary releases, blue-green deployments. Git becomes your source of truth. Deployments become automated, auditable, and rollbackable. See you then.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.